In the freezing blackness past Neptune, something massive may be pulling on dozens of icy worlds, herding them, tilting them, twisting their paths around the Sunday. Astronomers have been hunting it for over a decade. They call it Planet 9, a rocky giant, possibly 5 times heavier than Earth, hiding so far away that sunlight takes nearly 3 days to reach it. But here's the strange part. Its orbit shouldn't exist. It breaks the rules of how planets form. If you enjoy unsolved cosmic mysteries, hit subscribe. We have 33 of them ahead. Prepare yourselves. We begin. Far beyond Neptune, in a region so cold that nitrogen freezes solid, 6 small worlds were doing something they had no business doing. They were lined up. It was 2014. 2 astronomers, Chad Trujillo and Scott Shepard, were studying the most distant objects ever found in our solar system. These are called extreme trans-Neptunian objects, or distant icy bodies that orbit the Sun at staggering distances. We're talking about worlds that take 20,000 years to complete a single trip around our star. Worlds so far out that the Sun looks like a bright star, not a fireball. When Trujillo and Shepard plotted the orbits of these 6 objects on a map of the solar system, they froze. Every single one of them was tilted in the same direction. Every single one made its closest approach to the Sun in the same patch of sky. It was as if 6 different cars on 6 different highways had all decided to take the exact same exit at the exact same angle. Statistically, this should never happen. The odds of 6 independent objects randomly aligning this way were calculated at roughly 1 in 15,000. To put that in perspective, you have a better chance of being struck by lightning twice in your life than seeing this pattern by accident. So what was forcing them into formation? Picture a flock of birds flying in a perfect V. You don't need to see the wind to know something is shaping their path. The same logic applied here. Some unseen force, some massive object, was reaching across billions of miles and gently tugging these distant worlds into a synchronized dance. Whatever was doing this had to be huge, bigger than Earth, possibly bigger than Neptune. And it had to be hiding somewhere, out there in the dark, far beyond anything we'd ever mapped. Trujillo and Shepard wrote a careful paper. They suggested, very cautiously, that a planet might be responsible. The astronomy community paid attention but didn't go wild. After all, predicting a planet from orbital math was an old game, and most of those predictions had failed. But 2 researchers at Caltech read that paper and couldn't sleep. Mike Brown and Konstantin Batygin started running the numbers themselves. Brown is famous for being the man who killed Pluto, the astronomer whose discoveries forced Pluto to be downgraded from a planet to a dwarf planet. He was the last person you'd expect to add a new planet to the textbooks. He set out to disprove the hypothesis. He failed. Every simulation Brown and Batygin ran told them the same thing. The clustering was real, the 6 objects were being shepherded, and the shepherd was massive. Their math suggested a world roughly 5 to 10 times the mass of Earth, sitting in a wildly tilted orbit, hundreds of times farther from the Sun than our planet sits now. In January of 2016, they announced it to the world. They called it Planet 9. The discovery shocked everyone, including themselves. Here was a man who had built his career hunting tiny ice balls, suddenly claiming there was a hidden giant in our own backyard. The press exploded. Conspiracy theories bloomed online. Other astronomers split into believers and skeptics. Then, the discoveries started coming in. More icy worlds, more aligned orbits, more evidence that something massive was pulling strings from the shadows. And the deeper anyone looked, the stranger the picture became, because the next clue came from a place no one expected, the Sun itself. In 1846, astronomers were losing their minds over Uranus. The planet was doing something wrong. It kept drifting off course, slipping ahead of where the math said it should be, then falling behind. Newton's laws of gravity were the most tested theory in science, and Uranus was breaking them. Two mathematicians, working separately and not even speaking to each other, had the same wild idea. What if Uranus wasn't broken? What if something else, something we couldn't see, was pulling on it from the outside? They sat down with paper and pencil and calculated where this invisible object would have to be to produce the exact wobble Uranus showed. They each came up with nearly the same answer. A telescope in Berlin pointed at the predicted spot. On the very first night, they found it. A new planet. They called it Neptune. Think about how miraculous that was. A planet was discovered using only mathematics. Nobody saw it through a telescope first. Nobody stumbled across it by accident. They just predicted exactly where it had to be, looked, and there it was. It was one of the greatest triumphs of human reasoning in history. Now, fast forward almost 2 centuries. We have telescopes that can see galaxies forming when the universe was a baby. We've landed robots on Mars. We've sent probes flying past Pluto. And yet, the same exact technique that found Neptune may be about to find a brand new planet right now in our own solar system. The parallels are striking. Just like Uranus was tugging on Neptune's gravity, the distant icy worlds beyond Neptune are being tugged by something we can't see. The math is telling us where to look. The pattern is too clean to be a coincidence. But there's a catch, and it's a big one. When astronomers predicted Neptune, they had clean, easy data. Uranus was bright. It was visible in any decent telescope. Astronomers could measure exactly where it was in the sky on any given night. Predicting Neptune was hard, but the input data was solid. Planet 9 is a different beast entirely. The objects that suggest its existence are tiny, dim, and very far away. Some of them are barely brighter than a candle seen from across an ocean. Astronomers have to spot them, track them for years, and stitch together a picture of their orbits using whatever fragments of data they can scrape together. So while the technique is the same, the difficulty is hundreds of times higher. We're trying to find a needle in a haystack while standing in a different field, in the dark, during a snowstorm. There's another twist that makes this story stranger than Neptune's. When the Berlin astronomer pointed his telescope at the predicted spot for Neptune, he found it the very first night. With Planet 9, we've been searching for over 10 years now. We know roughly where to look. Surveys like WISE and Pan-STARRS have scanned huge chunks of sky. Nothing has shown up. That should mean Planet 9 isn't there. Or it should mean something even stranger is happening. Maybe it's farther than we thought. Maybe it's smaller. Maybe it's something we don't have a name for yet. And maybe, just maybe, the entire sun is leaning over because of it. Stand in front of a record player. The record spins flat. The needle traces circles on a flat surface. That's how the solar system is supposed to work. The sun spins, and all the planets should orbit in a flat plane lined up with the sun's equator. Clean, simple, neat. Except our solar system isn't neat. Not even close. If you measure carefully, the sun is tipped over. By 6 degrees, the sun's spin axis points one way, but every single planet, from tiny Mercury all the way out to Neptune, orbits in a plane that's tilted 6 degrees away from where it should be. Imagine a record player where the disc somehow floats 6 degrees off the turntable, but keeps spinning anyway. It's wrong. It's been wrong for as long as we've been watching. For decades, this was an embarrassment. Astronomers called it the solar obliquity problem. It was so awkward that, as Mike Brown of Caltech once admitted, scientists basically stopped talking about it. They had no good explanation, so they pretended it wasn't a big deal. Some suggested a passing star had nudged the sun long ago. Others guessed at magnetic fields tugging on the early solar system. None of these ideas held up under scrutiny. 6 degrees may sound small. It isn't. Over the 4.5 billion years our solar system has existed, that tilt represents an enormous transfer of angular momentum. Something physically massive had to push the sun and the planets out of alignment. Whatever did, it had to be working slowly, persistently, pulling for billions of years on end. Like a tiny child gradually tilting a heavy adult by leaning on their shoulder for a lifetime. In 2016, Brown and Battigan were sitting on their newly proposed Planet 9 when a graduate student named Elizabeth Bailey wandered in with an idea. What if Planet 9, sitting out there in its weird tilted orbit, was the thing that had been slowly tipping the rest of the solar system for billions of years? Bailey ran the simulations. The numbers fell into place almost too perfectly. If Planet 9 had a mass roughly 10 times Earth's and an orbit tilted about 30 degrees from the rest of the planets, then over 4 billion years, it would have wobbled the entire solar system by exactly 6 degrees. Not 5, not 7, 6. The match was uncanny. Here was a problem that had bothered astronomers for nearly 100 years, suddenly cracked by a hypothetical planet that had been proposed for completely unrelated reasons. It was as if you'd been trying to figure out why your house creaked at night for decades, and someone pointed out there was a giant sitting on your roof. But this raised a new question, an even weirder one. If Planet 9 is tipping the entire solar system, then what tipped Planet 9? You can't get a 30-degree tilt for free. Some violent event, some ancient gravitational mugging, must have thrown this world into its strange angled orbit billions of years ago. What was strong enough to do that, and where did it go? And there was another puzzle on the horizon. Mike Brown started getting strange phone calls, people who had been combing through old infrared sky surveys, looking for anything massive lurking far from the Sunday. They thought they might have found something, a faint dot, in a pair of pictures taken 23 years apart, that had moved exactly the way Planet 9 should move. Mike Brown didn't want to find a new planet. He'd already done the opposite. He was the astronomer who effectively killed Pluto's planetary status by finding Eris, a trans-Neptunian world roughly the same size as Pluto. That discovery forced the scientific community to redefine what a planet even is. Pluto got demoted. Brown got hate mail from elementary school students for years. He even wrote a book about it called How I Killed Pluto. So when he and Konstantin Batygin started seeing patterns in the distant Kuiper belt, Brown's first instinct was to be skeptical. Astronomers have predicted hidden planets in the outer solar system many times before. Percival Lowell spent years searching for a mythical planet X that turned out not to exist. Every generation seems to produce someone claiming there's a giant hiding past Neptune. Almost all of them have been wrong. Batygin was younger, sharper, and a theoretical specialist. Brown brought decades of observational experience. They worked in adjacent offices at Caltech, and at first they were trying to disprove the Trujillo and Shepard alignment paper from 2014. They thought it was probably a statistical fluke. They wanted to show that random chance could explain the clustering. It couldn't. For nearly 2 years, the pair ran simulation after simulation. They tried every possible explanation. Maybe Neptune had nudged the objects. No, the geometry was wrong. Maybe a passing star had done it. No, the timing didn't work. Maybe the icy worlds were in some kind of mutual gravitational dance with each other. No, they were too far apart to influence each other meaningfully. The only thing that fit the data was a single massive planet, sitting in a wildly tilted orbit, slowly herding the icy bodies into formation over billions of years. When they finally published their findings in January 2016, the announcement was carefully worded. They didn't say they'd found a planet. They said the data strongly implied one had to exist. Brown told reporters he was about 90% sure. Batygin was more measured, calling it a hypothesis with strong evidence. The world didn't care about their caution. Within hours, headlines around the planet were screaming about a hidden ninth world. Brown's email inbox flooded. Some messages were from amateur astronomers offering to help search. Others were from cranks claiming Planet 9 was a UFO, a black hole, or a sign of the apocalypse. One man insisted Brown had been hiding the planet for the government. Through all of it, Brown and Batygin kept working. They didn't have direct proof. They had inference. They had a pattern that demanded an explanation. So they started doing what any good scientist would do. They started predicting where Planet 9 should be, so other astronomers could try to photograph it. Their predictions narrowed over time. By 2025, refined simulations using 51 distant objects had pointed to a specific region of sky. The planet, if real, would be roughly 290 times farther from the Sun than Earth, and possibly within reach of upcoming telescopes. But every new piece of data brought new contradictions. The orbit predictions kept shifting. The mass kept changing. Some new discoveries supported the planet. Others seemed to argue against it. And then came the strangest twist of all. The shape of the orbit itself made no physical sense. Solar systems form according to a pretty simple recipe. A giant cloud of gas and dust collapses under its own weight, spins faster and faster as it shrinks, and flattens out into a thin disk. Planets form within that disk, like raisins baked into a pancake. They all end up moving in roughly the same direction, in roughly the same plane, on roughly circular orbits. That's how it's supposed to work. We see this happening right now around other stars. We have photographs of these flat, dusty disks with newborn planets carving out gaps inside them. The physics is solid. The pattern is universal. Planet 9 breaks every part of this pattern. Its predicted orbit isn't circular. It's wildly stretched, more like the long, thin shape of a comet's path than a planet's. At its closest, Planet 9 is thought to come within about 200 Earth-Sun distances of our star. At its farthest, it might swing out to nearly 400. That kind of stretched orbit, called highly eccentric, is normal for icy comets. It is not normal for a planet 5 or more times the mass of Earth. Then there's the tilt. The orbit isn't lined up with the rest of the planets. It's angled roughly 30 degrees off the main plane of the solar system. Imagine a spinning frisbee with a marble rolling around it on a steep diagonal track. That's roughly what Planet 9 is doing. None of the 8 known planets do anything like this. And finally, there's the distance. Even at its closest approach, Planet 9 sits hundreds of times farther from the Sun than Earth. The original solar system disk, the one that gave birth to Mercury, Venus, Earth, Mars, and the giants, only extended a fraction of that far. There simply wasn't enough material out at those distances to form a planet of this size in the first place. The disk thinned out and died before it ever reached Planet 9 territory. So, how did it get there? This is the puzzle that keeps astronomers up at night. You can't bake a planet where there's no batter. If Planet 9 formed in the outer solar system, the standard recipe says it shouldn't exist. Something had to put it there after the fact. There are a few possibilities. Each one is stranger than the last. Maybe Planet 9 formed close to the Sun, somewhere near Jupiter or Saturn, and got violently kicked outward by a gravitational encounter during the chaotic early years of the solar system. Maybe it formed around a different star entirely and our Sun stole it during a close stellar encounter billions of years ago. Maybe it was a rogue planet, drifting alone through interstellar space, that wandered too close to the Sun and got captured. None of these scenarios are easy. Each one requires very specific conditions, lucky timing, and a chain of events that has only a small probability of happening. Astronomers estimate the odds of any one of these scenarios at just a few percent. A few percent isn't impossible, but it isn't comfortable either. It means Planet 9, if real, is the result of a rare and violent past. A planet shaped by chaos rather than calm. A survivor of some ancient cosmic catastrophe whose details we can only guess at. And the deeper astronomers dig, the more catastrophic that past appears. For years, almost everyone assumed Planet 9 would be a small ice giant, something like a baby Neptune, full of frozen gases and surrounded by hydrogen and helium. That made sense. The outer solar system is cold. Cold places favor planets made of ice and gas. Uranus and Neptune fit this pattern. Whatever was lurking beyond them, the thinking went, probably did too. In 2025, that assumption fell apart. A team led by astronomer Amir Siraj working with veterans Christopher Chyba and Scott Tremaine, did the most comprehensive simulation of Planet 9 yet. They used data from 51 different distant icy bodies, far more than the original 6 that started the whole story. They ran 300 separate computer simulations. They tested every reasonable orbit and mass for the hidden planet. The result was startling. Planet 9, according to their math, was probably much closer than originally thought, roughly 290 times the Earth-Sun distance. Its mass came out to about 4 times Earth's, give or take a bit. And here was the kicker. Its predicted size and orbit suggested it was probably rocky, like Earth, rather than gassy, like Neptune. A rocky planet, 4 times the mass of Earth, hundreds of times farther from the Sun than we are. Now ask yourself a simple question. How does that exist? Rocky planets, in our textbook understanding, form in the inner part of solar systems where it's hot. Heat lets metals and silicates condense out of gas, but leaves ice and gases too volatile to clump together. That's why Mercury, Venus, Earth, and Mars are all small and rocky. They formed in the warm inner zone. The big gas and ice giants formed further out, where it was cold enough for hydrogen, helium, and water ice to pile up into massive planets. A rocky planet at 290 Earth-Sun distances violates this entire framework. There was no warm zone out there, ever. The original protoplanetary disk that built our solar system simply didn't extend that far. Even the most generous estimates put the edge of meaningful planet building at around 50 to 100 Earth-Sun distances. Past that, the disk was too thin, too cold, and too sparse to assemble anything substantial. So a rocky Planet 9 doesn't have a happy origin story. It must have moved. The most likely scenario, according to Siraj and others, is that Planet 9 formed close to the Sunday, maybe between Jupiter and Saturn, maybe even closer. It would have grown rocky and dense in the warm inner system. Then, during the violent youth of our solar system, when the giant planets were still settling into their final orbits, Planet 9 got too close to one of them, probably Jupiter. The encounter slingshotted it outward like a baseball off a bat, hurling it into the deep dark. If this happened, Planet 9 should have flown away forever. Most ejected planets do. They become rogue worlds, drifting alone through interstellar space, never to return. But something stopped Planet 9. Maybe a passing star tugged it just enough to pull it back. Maybe gas drag from the dying solar nebula slowed it down. Whatever happened, Planet 9 ended up trapped in an enormous looping orbit, frozen in place for the next 4.5 billion years. A rocky exile, a wanderer that almost escaped, but not quite. A survivor that shouldn't be there at all. And then, in 2025, someone may have actually photographed it. The discovery, if you can call it that, happened almost by accident. A team of astronomers in Taiwan was hunting through old infrared sky surveys for anything massive that might be hiding in the outer solar system. They had a clever idea: compare 2 very different surveys, taken decades apart. If a real planet was out there, it would be visible in both. But because it would be slowly moving along its orbit, it would appear in slightly different positions in each survey. Stars don't move, galaxies don't move. Anything that shifts position between 2 surveys taken decades apart is something local, something belonging to our own solar system. The team chose 2 surveys. The first was IRAS, the infrared astronomical satellite, which scanned the sky in 1983. The second was ACARI, a Japanese infrared telescope that mapped the heavens in 2006. 23 years separated the 2 surveys. That's plenty of time for a slow-moving outer planet to shift its position by a measurable amount. The astronomers ran software that compared the 2 maps. They were looking for a needle in a haystack, but a very specific kind of needle. An object that appeared at one spot in 1983 was completely missing 23 years later, but had a matching object in the second survey at a slightly different spot. A trail of 2 breadcrumbs separated by decades. After exhausting analysis, they found one. Just one. In the IRAS image from 1983, there was a faint infrared dot in a particular patch of sky. By the time Akari looked at the same spot in 2006, that dot was gone. But 47 arc-minutes away, Akari saw a new dot that hadn't been in the IRAS image. That distance, 47 arc-minutes, is roughly 1.5 times the width of the full moon as you see it from Earth. Could it be a coincidence? Could it be a glitch? Or a passing asteroid? Or a flaw in the data? The team checked. It didn't match any known asteroid. It didn't match any catalogued star or galaxy. The brightness of the object, its position, and the distance it appeared to have moved in 23 years all matched what astronomers expected for Planet 9. If real, this object would be roughly 700 times farther from the Sun than Earth. It would be larger than Neptune. It would have shifted its position in the sky by exactly the amount a slow, distant world should shift over 23 years. The team published their findings in 2025. The reaction was cautious excitement. Mike Brown himself looked at the data and said the candidate was interesting but not Planet 9 in the orbit he and Batygin had predicted. The position was off. The distance was different. If this was a real object, it might be an entirely separate hidden planet, one nobody had predicted. The catch is brutal. With only 2 snapshots taken 23 years apart, you can't fully calculate an orbit. You need at least 3 observations, ideally many more, to lock down an object's path. The candidate is just a hint. It needs to be recovered in modern telescopes. It needs to be tracked across multiple nights to confirm it's real and to nail down where it's heading. Until then, the moving dot remains a tantalizing maybe, a breadcrumb in the dark. But there are other breadcrumbs out there. Some of them have names, and one of them, called Sedna, has been begging for an explanation since the day it was found. In 2003, a small reddish world was found drifting at the edge of everything we knew. Astronomers named it Sedna, after the Inuit goddess of the icy seas. From the moment the discovery was announced, Sedna was a problem. Sedna doesn't behave like anything else in the solar system. Pluto orbits the Sun at about 30 Earth-Sun distances. Neptune sits at about 30 as well. Even the most distant Kuiper Belt objects loop out to maybe 50 or 60. Sedna, at its closest approach to the Sun, comes in at around 76 Earth-Sun distances. That's already remarkable. But Sedna's orbit is wildly stretched. At its farthest point, it sails out to about 937 Earth-Sun distances. A single orbit takes roughly 11,400 years. Now, consider what that means. Sedna, at its closest, is still far beyond Neptune. It never gets close enough for any known planet to influence it. Yet something put it on this huge, stretched orbit. Sedna couldn't have formed where it is. The disk that built our solar system never extended that far. It also can't have been pushed there by Neptune, because Neptune's reach doesn't go nearly far enough. So, what flung Sedna out there? And what keeps it from drifting away entirely? For years, the leading guess was that a passing star, billions of years ago, had tugged Sedna onto its strange orbit during a chaotic encounter in the early solar system. Maybe so, but Sedna wasn't alone for long. By 2012, astronomers had found another similar object, 2012 VP113, then more. By the late 2010s, a small family of Sedna-like worlds had been catalogued, each one with a similarly extreme orbit. These bodies came to be called sednoids, and they share an unsettling feature, like the original 6 objects that started the Planet 9 story, the Sednoids cluster. Their orbits aren't randomly oriented. They tend to point the same direction, with their closest approaches to the Sun falling in roughly the same patch of sky. This pattern is extremely hard to maintain by chance. Over billions of years, random gravitational nudges from passing stars and the slow drift of orbits should erase any clustering. Yet the Sednoids stay aligned. Something has to be actively maintaining the pattern. Something massive, something far away, something that pulls on each of these distant worlds just enough, every orbit, to keep them in formation. Planet 9 fits the role beautifully. A massive, distant planet looping along a stretched, tilted orbit would gravitationally nudge each sednoid back into alignment whenever it drifted out, like a sheepdog patrolling a flock. But Sedna also adds a wrinkle. Its closest approach distance, that 76 Earth-Sun figure, isn't just unusual, it's part of a strange gap. Astronomers have noticed that distant icy bodies tend to either come close to Neptune at 50 or 60 Earth-Sun distances, or stay far away at 70 or more. There's a curious empty zone in between, a perihelion gap, as it's called. Planet 9 could explain this gap. Its gravity would have cleared out objects whose orbits would otherwise have wandered into that range, like a janitor sweeping a hallway clean. Sedna alone is a mystery. The sednoids together are a pattern, and patterns demand explanations. Whatever force is keeping these worlds in line isn't going anywhere. It's still there, right now, watching, pulling, herding, and the strangest part is, it's not just gentle nudging. Some objects out there have been twisted into orbits that defy belief. Picture a vast pasture, miles wide, with a few dozen sheep scattered across it. Without a shepherd, those sheep wander. Some drift toward the river, some climb the hill, some get lost in the brush. They go wherever their feet take them. After a few days, you'd find them spread out at random across the field. Now, picture the same pasture with a single working sheepdog. That dog doesn't have to push every sheep into formation by hand. It just runs around the edges, snapping at strays, keeping the herd loosely contained. Over time, the sheep cluster, not because they planned to, but because something on the periphery is shaping their behavior. This is essentially what Planet 9 appears to be doing. The gravity of any planet, even a tiny one, reaches infinitely far in theory. In practice, it weakens fast with distance. By the time you get out to the realm of the icy distant bodies, a single planet's pull is incredibly weak. But weakness doesn't matter. What matters is consistency. Over hundreds of millions of years, even a faint, persistent tug can sculpt the orbits of distant objects into surprising shapes. When Brown and Battigan ran their simulations, they found that the math worked out almost too well. A massive planet on a tilted, stretched orbit, far beyond Neptune, would slowly herd icy bodies into very specific configurations. The closest approaches of the icy worlds would bunch up on one side of the Sunday. Their orbital tilts would tend to lean in one direction. Some objects would even get flipped onto orbits perpendicular to the rest of the solar system. The exciting part is that all of these effects are exactly what astronomers actually see. The clustering of orbits, the aligned closest approaches, the strange tilts, the flipped objects. The simulations match reality with eerie precision. There's a term for this kind of orbital herding. Astronomers call it shepherding, the same word ranchers use, because the metaphor is too perfect to resist. Saturn's rings have moons that act as shepherds, gravitationally nudging ring particles to keep them confined in narrow bands. Without those moons, the rings would spread out and dissipate. With the moons, the rings stay sharp and clean. Planet 9 appears to be doing the same thing on a vastly larger scale, herding icy worlds across billions of miles of empty space. But shepherding only works if the shepherd is consistent. A passing star wouldn't do it. A single ancient gravitational kick wouldn't do it. The patterns we see in the distant solar system require a planet that has been in roughly the same orbit for billions of years, gently pulling on the distant icy worlds every time they swing close. That's the strongest argument for Planet 9 being real, and not just a relic of some long-gone disturbance. The clustering hasn't faded. The patterns are as clean as ever. The shepherd is still on the job. There's a darker implication too. If Planet 9 vanished tomorrow, the clustering would slowly drift away over millions of years, and the distant icy worlds would scatter into chaos. The fact that we see them tightly grouped right now means the planet must still be there, right now, pulling the strings in real time. But shepherding isn't the only thing going on out there. Some objects haven't just been gathered up, they've been violently flipped onto orbits that point perpendicular to everything else. Worlds spinning sideways, worlds rolling end over end through the dark. One number keeps haunting astronomers: 30 degrees. Planet 9, according to every detailed simulation that matches the observations, has to sit on an orbit that's tilted roughly 30 degrees away from the main plane of the solar system. Not 5, not 10, around 30. That tilt is essential. Without it, Planet 9 wouldn't be able to produce the exact patterns of clustering, alignment, and warped orbits seen in the distant icy bodies. The number is locked in by the math, but 30 degrees is a problem, a big one. Remember the standard origin story for solar systems. A spinning cloud of gas collapses into a flat disk. Planets form in that disk, all moving in roughly the same direction, all orbiting in roughly the same plane. If you measure the 8 known planets, they're all within a couple of degrees of each other. They orbit in nearly the same plane because they were all born in the same flat, dusty pancake. Planet 9's 30-degree tilt is a screaming alarm bell. No planet that quietly formed in the original disk would end up tilted that much. To get an orbit angled that far off, something had to violently shove the planet onto its current path. Some catastrophic gravitational event. The leading idea is that Planet 9 got its tilt by being violently ejected from its original orbit by Jupiter or Saturn during the solar system's chaotic infancy. Imagine a young Planet 9 forming peacefully near Saturn when it gets too close to the giant. The encounter throws Planet 9 outward in a stretched, tilted orbit. The same encounter could have given Planet 9 its rocky composition, since it would have formed in the warm inner system before getting flung outward. This solves part of the problem. It explains how a planet ended up in such a strange orbit, but it creates a new headache. Most planets that get flung by Jupiter or Saturn don't just end up on weird orbits. They escape the solar system entirely. They become rogue planets, drifting forever through interstellar space. For Planet 9 to have stayed bound to the Sun, something had to slow it down at exactly the right moment. A passing star tugging on it gently, or drag from leftover gas in the dying solar nebula, or a perfectly timed gravitational nudge from another object. The odds of that happening, astronomers calculate, are around a few percent. Not impossible, not comfortable either. The 30-degree number also matters for another reason. Remember the 6-degree tilt of the Sun, the puzzle that bothered astronomers for nearly a century. When researchers ran simulations of how a tilted Planet 9 would influence the rest of the solar system over 4.5 billion years, the result was almost magical. A Planet 9 tilted 30 degrees produces a wobble that slowly tips the rest of the planets by exactly 6 degrees. So the 30-degree tilt isn't just a quirk. It's a key. It connects two seemingly unrelated mysteries: the orbits of the distant icy bodies and the leaning of the Sun, into a single coherent story. One rogue planet, one violent ancient encounter, one slow billion-year wobble. Everything snaps together. If Planet 9 isn't real, then we need entirely different explanations for both the distant orbital clustering and the Sun's tilt. So far, no one has come up with anything that works half as well. But Planet 9 isn't the only theory in town. Some scientists think the answer might involve no planet at all, but a hidden ring of mass, or even a small, ancient black hole. Try to picture the early solar system. It wasn't peaceful. It wasn't elegant. It was a demolition derby of half-formed worlds smashing into each other, gas giants migrating wildly, and small planets being thrown around like marbles in a blender. In the modern view, the 4 giant planets, Jupiter, Saturn, Uranus, and Neptune, didn't just settle quietly into their current orbits. They migrated. Jupiter probably formed farther from the Sun and drifted inward before swinging back out. Neptune formed closer and got pushed outward. During this chaotic era, the gas giants disturbed everything around them, scattering smaller planets like 10 pins in a bowling alley. This is where Planet 9's origin story most likely begins. If a fifth ice giant, slightly smaller than Neptune, was forming somewhere near the orbits of Saturn or Uranus during this chaos, it didn't have a pleasant childhood. The gas giants were enormous, and any planet that wandered too close to them would have felt their crushing gravitational pull. A close encounter with Jupiter, in particular, is the orbital equivalent of getting hit by a freight train. The giant planet's gravity is so strong that it can slingshot smaller worlds at tremendous speeds, sending them flying out of the inner solar system entirely. Most planets that suffer this kind of gravitational mugging end up ejected forever. They escape the sun's grip and drift off into interstellar space as rogue planets, doomed to wander alone for eternity. But every now and then, a planet gets a softer shove, just enough to throw it onto an enormous stretched orbit, but not quite enough to free it. That planet stays bound to the sun, but only barely. Its orbit becomes elongated, tilted, and far more distant than it ever was when it formed. Its closest approach might still be hundreds of Earth-Sun distances away. Its farthest approach might be more than 1,000. This is what Brown and Batygin think happened to Planet 9. It formed close to the Sunday. It got too close to Jupiter or Saturn. Jupiter slung it like a stone from a slingshot. The throw was almost hard enough to free it, but not quite. Planet 9 ended up on the long, lonely orbit it sits on today. The math for this scenario isn't easy. The slingshot has to be strong enough to get the planet outward, but not so strong that it escapes. The orbit has to be stretched enough to match the observed gravitational influence on distant icy bodies, but not so stretched that the planet would have been picked off by passing stars long ago. Threading this needle requires a fairly specific set of initial conditions. Some researchers have proposed an extra ingredient to make the math work. A passing star, maybe within a few hundred Earth-Sun distances, could have nudged Planet 9 just at the right moment to circularize and stabilize its orbit after the slingshot. Stars are common, especially early in our solar system's life, when our sun was probably still embedded in its birth cluster. Close stellar flybys would have happened regularly. Another possibility is that gas drag did the job. The early solar system was still full of leftover hydrogen and dust from the original collapsing cloud. A tilted, stretched Planet 9, plowing through this leftover gas, would have slowed down on each pass, gradually settling into a more stable orbit before the gas dissipated. Whatever the exact details, the slingshot story is the most popular Planet 9 origin theory. It explains the orbit, it explains the rocky composition, it even explains the tilt. But it isn't the only story being told. Some astronomers think Planet 9 wasn't ours to begin with. About 4.5 billion years ago, our sun wasn't alone. It was probably born in a tight cluster of hundreds or thousands of other young stars, packed together in a cosmic nursery. Those stars formed close enough that their gravitational fields constantly tugged on each other. Their planetary systems brushed against each other. Sometimes, they exchanged things. This is the scenario behind one of the most provocative theories about Planet 9. What if Planet 9 didn't form in our solar system at all? What if our young sun, during a close encounter with a passing star, simply stole it? The idea sounds wild, but the physics behind it is reasonable. In a tight star cluster, close stellar encounters happen all the time. When two stars pass within a few hundred Earth-Sun distances of each other, their gravitational fields can rip planets right off one star and capture them around the other. It's the cosmic version of two passing pickpockets exchanging wallets without breaking stride. Computer simulations show that capture is actually pretty common in dense young stellar nurseries. When researchers model what happens when a planet-bearing star swings past another planet-bearing star, they find that planets do switch teams. The captured planets typically end up on wide, stretched, tilted orbits. Exactly the kind of orbit Planet 9 appears to have. A captured Planet 9 would solve some of the trickiest parts of the puzzle. The strange orbit makes more sense if the planet didn't form in our solar system's original disk. The composition could be anything. since it inherited its makeup from a different star's protoplanetary environment. The 30-degree tilt is no longer suspicious. It's just the angle the planet happened to come in at when our sun grabbed it. There's an exoplanet that supports this theory. It's called HD 106906b, and it's a giant world orbiting a binary star system roughly 300 light-years away. The strange thing about this planet is that it sits hundreds of Earth-Sun distances from its host stars, on a stretched, tilted orbit that closely resembles what astronomers predict for Planet 9. Some researchers think HD 106906b may have been captured from a passing star, just like Planet 9 might have been. Here's the tricky part though. Capture requires very specific conditions. The two stars need to pass at exactly the right distance, at exactly the right speed, with exactly the right relative motion of their planets. Too close and the planet gets thrown into the new star and destroyed. Too far and nothing happens. Too fast and the planet stays with its original star. Too slow and the encounter takes too long, allowing the planet to settle back where it came from. Estimates suggest that capture is responsible for only a small fraction of distant exoplanets, but a small fraction of trillions of stellar encounters across the galaxy still adds up to a lot of stolen worlds. If our young sun spent its first 100 million years in a crowded star cluster, there were plenty of opportunities to swipe a passing planet. If Planet 9 is a captured world, it would be a piece of an entirely different solar system, hidden in our own, a relic of an alien place, a planet whose minerals, atmosphere, and history come from circling a star that no longer exists in our neighborhood. We'd be sharing our solar system with a refugee. There's a third possibility for Planet 9's origin that's even stranger than the first two. Not slung by Jupiter, not stolen from another star. Maybe Planet 9 was a rogue. Rogue planets are worlds without stars. They drift through interstellar space alone, untethered to any solar system, freezing in the dark. For a long time, scientists assumed they were rare. Recent surveys suggest the opposite. Our galaxy may contain trillions of these starless wanderers. Some estimates put the number of rogue planets higher than the number of stars themselves. Our Milky Way is awash in them. Most rogue planets started life in normal solar systems. They formed in the protoplanetary disks of young stars, just like Earth or Jupiter. But during the chaotic early years, gravitational encounters with other planets or passing stars threw them out of their birth systems. Once they cleared their host star's gravity, they were free. They became planetary drifters. A drifter can travel for billions of years without ever passing close to another star. Space is enormous. Stars are tiny dots in a vast emptiness. The odds of a wandering planet stumbling into another star system are extremely small, but not zero. Once in a great while, a rogue planet does drift close to a star. If the geometry is right, the star's gravity captures it. The planet stops being a rogue. It becomes part of a new solar system, even though it had nothing to do with the original formation of that system. Could Planet 9 be a captured rogue? Some astronomers think so. The capture scenario explains the strange orbit, the unusual tilt, and the fact that Planet 9 doesn't fit neatly into the original solar system's blueprint. It would be a stranger that arrived after the construction was finished. The math for capturing a rogue planet is harder than for capturing a planet from a passing star. Rogues tend to move fast relative to the sun, since they've been drifting for billions of years and have built up speed from countless gravitational interactions. A fast-moving rogue would just zip past the sun without slowing down enough to be captured. To stick around, the rogue would need to be moving slowly, ideally in roughly the same direction as the sun's motion, and it would need a third body to absorb some of its energy. A passing star, or perhaps the gas of the early solar nebula, could have done that job. The capture scenario has some attractive features. It would explain why Planet 9 seems too far out to have formed in our original disk. It would explain why its orbit is so tilted. It might even explain the rocky composition, since the original solar system that birthed Planet 9 would have had its own warm inner zone where rocky planets could form. But there's a chilling aspect to this theory. If Planet 9 is a captured rogue, then it is an outsider, and its history isn't tied to ours. The minerals on its surface, if it has a surface, would have formed around a different star. The light it once received came from a different sun. It is a piece of a vanished solar system, frozen and silent, now circling a star that adopted it billions of years after its birth. It would be the ultimate cosmic foundling, a child of a long-dead family, raised by strangers. But what if Planet 9 isn't a planet at all? What if it's something far more extreme? In 2020, two physicists, Jakob Schultz and James Unwin, published a paper that turned the Planet 9 debate upside down. They argued that the gravitational evidence for Planet 9 could equally well be explained by a tiny ancient black hole. Not a stellar black hole, the kind formed when a giant star collapses. Those are the size of small cities and weigh several times the mass of the Sunday. What Schultz and Unwin proposed was a primordial black hole, a relic from the first moments of the universe, when conditions were so extreme that small chunks of space-time could collapse on their own without needing a star to die. Primordial black holes, if they exist, would be exotic objects. They'd weigh roughly the same as Planet 9, around 5 to 10 Earth masses. But because of how compressed they are, their physical size would be astonishingly small. A 5 Earth mass primordial black hole would be roughly the size of a softball. You could hold one in your hands, except you absolutely couldn't, because it would devour your hands and the rest of the planet you were standing on. If our solar system captured one of these objects billions of years ago, it would behave gravitationally just like Planet 9. It would shepherd the icy worlds. It would tilt the Sunday. It would produce all the patterns astronomers have observed. The math is essentially identical. The only way to tell the difference between a planet and a primordial black hole would be by direct observation. A planet, even a cold one, reflects a tiny amount of sunlight. We could, in principle, photograph it with a sensitive enough telescope. A black hole reflects nothing. It is darker than the dark. You couldn't see it directly, ever. You could only detect it by what it does to light or matter passing nearby. This explains a frustrating mystery. If Planet 9 is a regular planet, why hasn't anyone photographed it yet? Several powerful sky surveys have hunted for it, including the Wide Field Infrared Survey Explorer and Pan-STARRS. They haven't found it. Maybe it's because the planet is very far away or very dark, but maybe it's because there's no planet to find at all. Maybe the real culprit is something invisible. Schultz and Unwin proposed a way to test the black hole idea. Even though a primordial black hole emits no light of its own, it would interact with surrounding dark matter, and that interaction could produce faint flashes of high-energy gamma radiation. A sensitive enough gamma-ray telescope could spot those flashes if they happened in the right place at the right time. Theoretical physicist Edward Witten took the idea a step further. He proposed sending a fleet of tiny probes, accelerated to high speeds by lasers, out into the regions where Planet 9 might be. Each probe would carry simple instruments. As they passed near a hidden mass, their trajectories would shift slightly due to the gravitational pull. By comparing the paths of many probes, scientists could pinpoint the location of the hidden object. The fleet idea remains theoretical. The technology to launch enough probes to a region hundreds of Earth-Sun distances away doesn't exist yet. But the very fact that serious physicists are debating whether our solar system might contain a primordial black hole tells you how unusual this situation is. Konstantin Batygin himself has weighed in on the black hole idea. He says it's possible. He also says there's no evidence to favor it over a regular planet. For now, both options remain on the table. But there are other clues. Some objects out there don't just orbit oddly, they orbit completely sideways. In the standard map of the solar system, almost every object orbits the Sun in roughly the same direction. Looking down from above the Sun's north pole, you'd see Mercury, Venus, Earth, and all the rest sweeping counterclockwise around our star. Their orbital planes are nearly aligned. The whole system looks like a flat plate spinning in a single direction. Now imagine throwing a marble onto that spinning plate at right angles, so the marble rolls in a perpendicular direction. That's roughly what some objects in the outer solar system are doing. They orbit the Sun at angles of around 90 degrees to everything else. They roll over the top and bottom of the solar system, rather than gliding around its edges. These perpendicular bodies were a complete surprise when they were first found. There was no natural way for objects to end up on such extreme orbits. The original protoplanetary disk was flat. Anything born in the disk should have inherited that flatness. To get a perpendicular orbit, you'd need a violent shove, something powerful enough to flip an icy world entirely on its side. Brown and Batygin checked whether Planet 9 could explain these perpendicular orbits. The answer turned out to be yes, and it did so without any tweaking of the model. Their original Planet 9 simulations, designed only to explain the clustering of distant icy bodies, also naturally produced perpendicular orbits as a side effect. How does that work? It comes down to a phenomenon called orbital resonance. When a small object regularly passes near a much larger one, their gravitational interactions can lock into specific patterns. Over millions of years, those patterns can shift the small object's orbit dramatically. In some configurations, Planet 9's gravity gradually tips an icy world's orbit further and further out of the main solar system plane until, eventually, the object is rolling at a right angle. This isn't a rare effect in the simulations. It's predicted to happen to a noticeable fraction of the most distant icy bodies. And when astronomers searched for these perpendicular objects, they found them. Several distant icy bodies with orbits tilted close to 90 degrees have been catalogued. Their existence had been a mystery for years before Planet 9 was proposed. For Brown, this was one of the most convincing pieces of evidence. He had originally tried to disprove the Planet 9 hypothesis. He kept running simulations, expecting to find that the planet wasn't needed. Instead, every new prediction the model made turned out to match real observations. The perpendicular bodies were the breaking point. There was no natural way to produce them without something like Planet 9, and the model had predicted them before they were even searched for systematically. There's something poetic about these sideways worlds. They're the cosmic equivalent of a flag pointing in an unexpected direction. A few billion years ago, they were probably ordinary, distant icy bodies orbiting peacefully in the main plane of the solar system. Then, slowly, century by century, Planet 9's gravity tugged them onto their bizarre paths, each one a witness to a hidden hand, each one a fingerprint left at a cosmic crime scene. If you could stand on the surface of one of these perpendicular bodies, you'd see the sun moving through the sky in a way no astronaut has ever experienced. The familiar plane of the planets would sweep past your zenith, with Jupiter, Saturn, Uranus, and Neptune all glinting in a tilted band overhead. You'd be on a world rolling at right angles to everything else, kicked there by something massive and mostly invisible. And the closer astronomers looked, the more strange features appeared. In 2024, Brown and Batygin published yet another piece of evidence for Planet 9, and this one came from an unexpected place. They found a gap, an empty region where icy worlds should have been, but weren't. To understand what they found, you have to remember that distant icy bodies don't all orbit the same way. Some have closest approaches to the Sun near Neptune, around 30 to 40 Earth-Sun distances. Others have closest approaches much farther out, 60, 70, or more. When you plot the closest approach distances of all known distant icy bodies, you'd expect to see a smooth distribution. Lots of objects close to Neptune, some farther out, gradually thinning as you go. That's not what we see. Instead, there's a strange empty zone, a perihelion gap, as astronomers call it. There are plenty of icy worlds with closest approaches near Neptune. There are also plenty with closest approaches far beyond, in the Sedna range. But the middle ground, between roughly 50 and 60 Earth-Sun distances, is unusually sparse. Far fewer objects than you'd expect. Why would there be a missing zone? When Brown and Batygin ran simulations of Planet Nine's gravitational influence, the gap appeared automatically. Their tilted, distant planet, simply by existing, sweeps clean a specific range of closest approach distances. Objects that wander into the gap zone get nudged out, either inward toward Neptune or outward into Sedna territory. Over billions of years, the result is exactly the empty band we see in the data. This was a powerful test for the Planet 9 hypothesis. Brown and Batygin hadn't designed their model to produce a gap. The model produced one anyway. And when they checked the actual catalogue of distant icy bodies, the gap was there, in the right place, with roughly the right depth. Brown said in interviews that he hadn't thought about the gap when he and Batygin first proposed Planet 9 in 2016. It hadn't been on their radar. They quickly realized that the gap was a natural consequence of the model. Once they worked out the math, the prediction matched the data. It felt like getting a free win. Skeptics weren't entirely convinced. Some pointed out that the catalogue of distant icy bodies is incomplete. We've only mapped a small fraction of what's actually out there. The apparent gap might not be a real gap at all. It might just be a sampling bias, where our telescopes are better at finding objects in certain orbital regions and worse at finding objects in others. This is a fair criticism. Astronomy in the outer solar system is hard. Distant icy bodies are tiny, dim, and slow-moving. They're easy to miss. Surveys tend to look at certain patches of sky for certain amounts of time, and they can systematically overlook objects with particular orbital configurations. Without a more complete catalogue, it's tough to be absolutely certain whether the gap is real or an artifact. But the gap argument doesn't have to stand alone. It joins a growing list of independent puzzles that all point in the same direction. The clustering of orbits, the aligned closest approaches, the sideways worlds, the sun's tilt, the strange behavior of objects like Sedna. Each one, on its own, could have other explanations. Together, they form a pattern that's tough to dismiss. The gap was the third major piece of evidence Brown and Batygin had assembled. Each piece had emerged from different observations, different methods, different parts of the data. Each one independently pointed to a hidden planet. The gap, when it appeared, felt to them like a final confirmation. Then a brand new discovery threatened to undo everything. In May of 2025, a team led by astrophysicist Zhihao Cheng announced the discovery of a new dwarf planet. They named it 2017 OF201. It was a serious find. The object is large, possibly several hundred miles across, and it sits on an extreme stretched orbit deep in the outer solar system. But here's the part that made everyone stop and stare. 2017 OF201 didn't fit the pattern. Every other distant icy world that supports the Planet 9 hypothesis shares specific features: stretched orbits, aligned closest approaches, tilted angles that bunch together. The clustering is what gives away the existence of an unseen shepherd. Cheng's new dwarf planet broke that pattern. Its orbit was wildly different from the rest. It didn't cluster with anything. It didn't align with the Planet 9 predicted patterns. It looked more like a wild card, an object that had wandered into the deep solar system from somewhere unexpected. This was a problem. If Planet 9 has been gravitationally herding distant icy bodies for billions of years, then any object hanging out in the deep outer system should bear the marks of that shepherding. Its orbit should be aligned with the others. Its closest approach should fall in the predicted region. 2017 OF201 doesn't. It's a sheep that ignored the dog. Cheng pointed out that, under the Planet 9 model, the new dwarf planet should have been disrupted by the hidden world's gravity long ago, either flung out of the solar system or absorbed into the cluster. Yet there it sat, cheerfully off-pattern, contradicting the predictions. There were a few possible explanations. The gentlest one was that 2017 OF201 had only recently arrived in its current orbit, perhaps nudged into place by a passing star within the last few million years. If that was the case, Planet 9 wouldn't have had time to either disrupt or align it yet. The dwarf planet would essentially be a fresh arrival, still in the process of being incorporated into the larger gravitational dance. Another explanation was less comfortable for Planet 9 fans. Maybe Planet 9 isn't where Brown and Batygin think it is. Maybe its orbit is different. Maybe its mass is different. Or maybe, in the worst case, Planet 9 doesn't exist at all, and the apparent clustering of other icy bodies has a different cause that doesn't extend to objects like 2017 OF 201. For Brown and Batygin, the discovery was a wake-up call. Their hypothesis had to be flexible enough to account for occasional outliers without losing its predictive power. They argued that occasional misfits don't disprove the model. Most of the distant icy bodies still cluster. The patterns are still there. 2017 OF 201 is one rebel in a population of conformists. But the discovery was a reminder of something important. The Planet 9 hypothesis is built on a small number of observed objects. Around 50 extreme distant icy bodies have been found and well studied. That's a tiny sample. Statistical patterns drawn from small samples can be misleading. A few new discoveries that go the wrong way could shift the picture significantly. And many more discoveries are coming. The next generation of telescopes is about to flood astronomers with new icy bodies. The catalogue will grow tenfold, perhaps 100-fold, in the next decade. Whether Planet 9 survives that scrutiny is one of the biggest open questions in astronomy, but 2017 OF 201 isn't the only object that doesn't fit. Just months later, another rebel turned up. Just months after the discovery of the rebel dwarf planet, another oddity emerged. A team announced a new icy world called 2023, KQ-14. The astronomers nicknamed it Ammonite, after the spiral-shelled sea creatures that once filled ancient oceans. Ammonite was unusual right from the start. It belongs to the small family of sednoids, the most extreme distant icy bodies known. Like Sedna itself, Ammonite has a stretched orbit and a closest approach to the Sun far beyond Neptune. So far, so familiar. The trouble is in the direction. Every previously discovered sednoid points its closest approach in roughly the same patch of sky. That alignment is one of the foundational pieces of evidence for Planet 9. The Shepherd planet, sitting in its tilted orbit, gravitationally tugs the icy worlds into a synchronized formation. Their closest approaches all face one direction. Their orbital tilts cluster together. The pattern is the fingerprint that gives the Shepherd away. Ammonite doesn't follow the pattern. Its closest approach to the Sun points the opposite direction from the other sednoids. While its cousins all face one side of the sky, Ammonite faces the other. It's as if a flock of birds was flying north and a single rebel decided to fly south. Even worse, simulations show that Ammonite's orbit has been stable for 4.5 billion years. It hasn't drifted into its current configuration recently. It's been there essentially since the beginning of the solar system, holding its contrarian position while everything else lined up. If Planet 9 exists with the orbit Brown and Batygin originally proposed, Ammonite shouldn't exist. Or rather, Ammonite should have either drifted into alignment with the other sednoids long ago or been gravitationally evicted entirely. The fact that it's been quietly sitting there, pointing the wrong way for 4 billion years, suggests either Planet 9 isn't doing what we think, or Planet 9's orbit is different from current predictions, or Planet 9 isn't there at all. Astronomers responded to Ammonite in different ways. Some saw it as a serious blow to the Planet 9 hypothesis. They argued that the icy world's stable, contrary orbit was strong evidence against any Shepherd planet powerful enough to maintain the alignment of the other sednoids. Others saw Ammonite as a constraint, not a refutation. The discovery, they said, simply tightens the range of possible orbits Planet 9 could have. The hidden planet isn't ruled out. It just has to be smaller or farther or differently oriented than initially thought. This kind of give and take is part of how science works. A hypothesis makes predictions. New data either supports those predictions or pushes them in new directions. Each new discovery refines the picture. Planet 9 has been refined many times since 2016, and it'll be refined more before any final answer arrives. Ammonite added another wrinkle. The icy world fills a particular gap in the previously known Sednoid orbits. Its position completes a pattern that, in some interpretations, is more easily explained by random scattering from passing stars long ago than by ongoing shepherding by a hidden planet. In other words, maybe the Sednoids aren't being herded at all. Maybe they're just frozen relics of an ancient, chaotic past. If that's the case, the entire Planet 9 story might collapse. The clustering would be a fossil of past events, not a sign of a present-day shepherd. The hidden planet could be a ghost. But Brown and Batygin weren't ready to give up. Each new wrinkle, they argued, was an opportunity to refine the model. The hunt was only getting more interesting. Even as the planet's predicted size kept shrinking, when Mike Brown and Konstantin Batygin first announced Planet 9 in 2016, they pictured a world roughly 10 times the mass of Earth. Maybe a small ice giant, like a baby Neptune. The orbit they predicted stretched out from about 400 to 800 Earth-Sun distances. Big planet, big orbit, big drama. By 2021, the picture had shifted. New simulations using more icy world data suggested Planet 9 was probably closer than originally thought. The semi-major axis, the average distance from the Sun, was revised downward to around 380 Earth-Sun distances. Still enormous, but noticeably smaller. Then came another revision, then another. By 2025, a major new study by Amir Siraj, Christopher Chyba, and Scott Tremaine had refined the numbers again. Their new model put Planet 9's average distance at around 290 Earth-Sun distances. They estimated the planet's mass at roughly 4.4 times Earth's, give or take. A noticeable shrink from the original 10 Earth masses. This trend has been a quiet embarrassment for the Planet 9 hypothesis. Each revision makes the planet smaller, closer, and easier to find. So why hasn't anyone found it yet? Part of the answer is that Planet 9 hunters have been running out of places to look. Each major sky survey eliminates regions where Planet 9 could be hiding, based on its predicted size and brightness. As the candidate parameters shift, the search areas shift too. If the planet were really 10 times Earth's mass and 400 Earth-Sun distances out, it would have been bright enough to spot in earlier surveys. The fact that it wasn't seen pushed the predictions towards smaller, dimmer, more distant configurations. The shrinking trend is partly observational. The more sky we search, the more we constrain what Planet 9 can be. Anything bright enough to see has already been ruled out. Whatever's left has to be on the dim side, smaller, darker, or farther, or all three. There's a deeper concern lurking in this pattern. At some point, if the predicted size of Planet 9 keeps shrinking, the planet stops being able to do what it was supposed to do in the first place. A 4 Earth mass world at 290 Earth-Sun distances exerts a much weaker gravitational influence than the 10 Earth mass giant originally proposed. The shepherding effect that's supposed to align the distant icy bodies depends on the planet being big enough to dominate their gravity over billions of years. A weaker planet might not be able to maintain the patterns we see. Some astronomers have started asking whether the entire Planet 9 framework is being slowly stretched to fit shifting data. As predictions narrow, are they narrowing towards something real, or are they being pruned to match whatever the latest survey hasn't found? Brown and Batygin maintain that the refinements are healthy science. The hypothesis is being constrained by data, not invented from scratch. The shrinking mass is uncomfortable, but not fatal. Their 2025 paper points out that even a 4 Earth mass planet, if positioned correctly, can produce most of the observed effects. The shrinking giant trend has another side. A smaller, closer Planet 9 becomes harder to spot if it's faint, but easier to spot if it has the right reflectivity. The 290 Earth-Sun figure puts Planet 9 within striking distance of the next generation of telescopes. The Vera Rubin Observatory, in particular, should be able to catch it within its early years of operation if it exists in roughly the predicted location. If that telescope finds nothing, the shrinking will continue, and eventually, if Planet 9 keeps getting smaller and closer with each new study, it might shrink right out of existence. But before that happens, another discovery emerged. In October of 2025, a team led by Amir Siraj proposed a brand new candidate for a hidden world. They called it Planet Y. The story behind it is different from Planet 9, and it might be even more uncomfortable. The team had been studying a different population of icy bodies, not the extreme distant ones that motivated Planet 9, but a closer group of objects in the Kuiper Belt, the broad ring of frozen worlds that stretches from Neptune outward to roughly 50 Earth-Sun distances. When Siraj and his collaborators carefully analyzed about 50 Kuiper Belt objects, they noticed something strange. The orbits were tilted, not violently, but unmistakably, in a way that suggested something was disturbing them. This tilt couldn't be explained by Planet 9. The hypothetical Planet 9 sits much farther out, beyond hundreds of Earth-Sun distances. Its gravity influences the most distant icy bodies, but it's too weak to noticeably tilt the closer Kuiper Belt population. Something else, the team concluded, must be tugging on these closer worlds. After running computer simulations, Siraj's team proposed a different planet, smaller than Planet 9, closer than Planet 9, tilted at least 10 degrees from the main solar system plane, mass somewhere between Mercury and Earth, distance between 100 and 200 Earth-Sun distances. They called it Planet Y to distinguish it from Planet 9, and the name caused some confusion. There's already a hypothetical Planet X from the early 1900s. There's Planet 9, now Planet Y. The naming scheme is starting to look like an alphabet soup of unproven worlds, but the science behind Planet Y is independent of Planet 9's evidence. The two planets, if they exist, would explain different mysteries. Planet Y, if real, would be a small rocky world tucked closer in than Planet 9. It would tug on Kuiper Belt objects gently, twisting their orbits over billions of years. It wouldn't be massive enough to herd the most distant sednoids, but it would be massive enough to leave fingerprints on the closer population. The statistical confidence for Planet Y is moderate. Siraj estimated it at around 96 to 98%. That's strong, but not airtight. With only 50 Kuiper Belt objects in the sample, the pattern might be a fluke. More objects need to be found and analyzed before Planet Y can be considered a serious detection. The discovery raises an unsettling question. If Planet Y exists alongside Planet 9, does that mean the outer solar system has multiple hidden worlds? It's possible. Theorists have argued for years that the outer solar system might contain more than one undiscovered planet. Each one might explain a different orbital pattern. The total population of hidden worlds could include not just Planet 9 and Planet Y, but possibly others, each one shepherding a different subset of icy bodies. If that's true, our solar system has more planets than we ever knew. The cosmic backyard is bigger and stranger than the textbooks let on. The famous count of 8 planets, plus dwarf Pluto, might be missing several major members. The next decade of astronomy could fundamentally rewrite the family portrait. Siraj's team noted that the Vera Rubin Observatory should be able to test the Planet Y hypothesis within its first few years of operation. Like Planet 9, Planet Y is well within the telescope's detection range, if it exists at the predicted distance and brightness. But Planet Y wasn't the only fresh evidence to emerge. The Kuiper Belt itself was warping in a way no one had predicted. The Kuiper Belt is sometimes called the third zone of our solar system. The first is the rocky inner planets, from Mercury through Mars. The second is the gas and ice giants, Jupiter through Neptune. The third is the icy frontier beyond Neptune, where Pluto and thousands of other frozen bodies orbit in a wide ring. The Kuiper Belt was first proposed in the 1940s and confirmed in the 1990s. For decades, astronomers assumed the Kuiper Belt was flat. The belt should sit roughly in the same plane as the 8 major planets, since it formed from the same protoplanetary disk. Any deviations from flatness should be small and easily explained by the gravitational pulls of the giant planets, especially Neptune. That picture was elegant. It was also wrong. Recent studies have shown that the Kuiper Belt isn't flat. It's warped. The orbital plane of the belt tilts by varying amounts depending on how far out you look. Closer to Neptune, the belt is roughly aligned with the main planetary plane. Farther out, the tilt grows. By the time you reach the outer edges, the average orbital plane of the belt is noticeably twisted away from where it should be. A warped Kuiper Belt isn't just an aesthetic curiosity, it's a clue. Something has to be pulling the outer parts of the belt out of alignment. Neptune isn't strong enough to do it across such large distances. Passing stars don't fit either, because their effects would be random and short-lived. The warp is consistent and structured, suggesting an ongoing influence. A massive, tilted, hidden planet is exactly the kind of thing that could produce a warp like this. If Planet 9, or Planet Y, or some combination of hidden worlds, has been quietly tugging on the Kuiper Belt for billions of years, the belt's outer regions would slowly bend toward their orbital planes. Over a long enough time, the bend would become noticeable, which is exactly what we see. The warp adds another layer of evidence to the hidden planet story. It's independent of the clustering of distant icy bodies. It's independent of the sun's tilt. It's independent of the perpendicular orbits and the perihelion gap. The warp comes from a different population of objects, analyzed in a different way, and it points to the same conclusion. Something out there is pulling on the outer solar system. Skeptics have alternative explanations. Some argue the warp could be a leftover from a long-gone disturbance, perhaps a passing star billions of years ago. Others suggest the warp might be an observational illusion caused by sampling biases in our incomplete catalogue of Kuiper Belt objects. These criticisms are valid. The warp evidence isn't conclusive on its own, but it's consistent. And the more independent lines of evidence point in the same direction, the harder it becomes to dismiss the whole picture. The warp joins the clustering, the gap, the sun's tilt, and the perpendicular orbits as another piece of a puzzle that increasingly demands a hidden gravitational force. The strange thing about the warp is its scale. We're talking about distortions that span tens of billions of miles. Whatever is causing the warp has been doing it for nearly the entire age of the solar system. The patient, persistent gravitational pull of a hidden world has slowly rearranged the geometry of everything beyond Neptune. If you could see gravity, the warp would be a fingerprint, a faint, smeared mark across the outer solar system, telling you that something massive has been touching everything for 4.5 billion years. But our solar system isn't unique. Other stars have their own hidden giants. In 2013, astronomers discovered a strange exoplanet around a binary star system roughly 300 light-years from Earth. They named it HD 106906b. The planet was a giant, about 11 times the mass of Jupiter, but its orbit was the unusual part. It sits at roughly 700 Earth-Sun distances from its host stars. Its orbital plane is tilted dramatically away from the dust disk surrounding the system. For years, HD 106906b was a curiosity. Planets aren't supposed to form that far from their host stars. The protoplanetary disks of stars rarely extend that far, and even when they do, there usually isn't enough material to build a giant planet at such enormous distances. The planet's existence was a puzzle. Then Planet 9 was proposed. Suddenly, HD 106906b stopped being an oddity and became a possible twin. The parallels are striking. Both planets sit hundreds of Earth-Sun distances from their stars. Both have stretched, tilted orbits. Both are plausibly the result of being violently scattered by a closer giant planet, then nudged back into bound orbits by a passing star. The mechanisms that might have produced HD 106906b's strange orbit are the same mechanisms that could have produced Planet 9's. This is important because it shows that the formation scenarios for Planet 9 aren't just theoretical fantasies. They actually happen. We can see the proof, sort of, around another star. Wide orbit planets exist. They've been photographed. Their orbits have been measured. They behave in ways consistent with models of violent scattering plus gentle stabilization. A planetary scientist named Sean Raymond and his colleagues have argued that wide orbit planets are probably common. Their simulations suggest that the chaotic early phases of solar system formation routinely fling planets into wide-stretched orbits. Most of those planets end up escaping their host stars entirely, becoming rogue worlds. But a small fraction, perhaps a few percent, get stabilized into bound orbits. Over the lifetime of the galaxy, this means there should be many wide-orbit planets out there. Recent surveys back this up. A few dozen exoplanets have now been discovered in wide-orbit configurations, hundreds or even thousands of Earth-Sun distances from their host stars. They're not common. They're not rare either. They occupy a real but limited slice of the exoplanet population. The fact that they exist at all is good news for the Planet 9 hypothesis. There's a second exoplanet that has caught attention as another possible Planet 9 analog. It's called BD plus 601417, and its orbit is similar in size and stretch to what Planet 9's predicted orbit, like HD 106906b. It serves as a real-world example that planets can exist in this regime. They're not just figments of our orbital simulations. If Planet 9 exists, it would join a small but growing club of distant wide-orbit worlds. Each one would be a survivor of some violent, ancient encounter, a planet that was kicked outward and somehow managed not to escape entirely. They'd be cosmic refugees, tied to their stars by the thinnest of gravitational threads. The existence of this club tells us something hopeful. The kind of planet we're looking for in our own solar system is a real category of object. It happens, it's been seen, it can be photographed. But finding our own version is a different challenge. It's nearby and dim, rather than far away and bright. To catch a faint dot moving slowly across the sky, astronomers need a telescope of extraordinary sensitivity. For nearly a decade, astronomers have been hunting for Planet 9. The search hasn't been casual. Major teams using powerful telescopes have systematically scanned huge regions of the sky. Why hasn't anyone found it? The first big search effort used data from the Wide Field Infrared Survey Explorer, a NASA space telescope launched in 2009. WISE scanned the entire sky in infrared, looking for warm and cool objects that ground-based telescopes might miss. Cold, distant planets emit very little visible light, but they radiate detectable amounts of infrared heat. WISE was designed to find them. The mission did find some interesting things. It catalogued thousands of new asteroids and comets. It discovered cold brown dwarfs, failed stars too small to ignite fusion. It found nothing that fit the profile of Planet 9 at the predicted distance and mass. Some astronomers initially took this as strong evidence against the planet's existence. WISE was sensitive enough to detect a Neptune-sized world out to about 10,000 Earth-Sun distances. If Planet 9 were big and bright, WISE should have caught it. But Planet 9, in its more recent shrunken form, may have been too small for WISE. A 4-Earth mass rocky planet, far colder than Neptune, would have radiated less infrared heat than the original predictions assumed. It might have slipped below WISE's detection threshold. The planet hunters didn't necessarily lose. They simply hadn't gone deep enough. Pan-STARRS, a ground-based telescope in Hawaii, conducted another major survey looking for distant solar system objects. It's a sensitive instrument with wide field coverage, It's discovered thousands of trans-Neptunian objects, including many that contributed to the Planet 9 hypothesis itself. But it didn't find the planet. This isn't entirely surprising. Pan-STARRS doesn't cover the whole sky. It also has limitations on how dim an object it can detect. If Planet 9 sits in a part of the sky that Pan-STARRS hasn't surveyed deeply, or if it's too faint, the telescope might have walked right past it without noticing. The southern sky is particularly tricky. For most professional observatories in the northern hemisphere, the southern sky is hard or impossible to see. The most likely orbital regions for Planet 9, based on Brown and Batygin's predictions, fall partly in the southern sky. Surveys based in the north have systematically missed those regions. There's also the matter of timing. Planet 9, if it exists, moves very slowly across the sky because it's so far away. To detect a slow-moving object, you typically need to take multiple images of the same patch of sky over months or years and look for tiny shifts. That kind of careful, long baseline monitoring is exactly what most existing surveys aren't designed for. The earlier searches weren't optimized for the very specific challenge of finding a distant, slow, dim planet. A more subtle problem is that Planet 9, even at its predicted distance, would still be faint, not invisible, but close to it. Its brightness would be at the very edge of what most telescopes can pick up. If the planet happens to be currently sitting at the more distant part of its stretched orbit, it would be even fainter, possibly below the detection limits of every survey conducted so far. In other words, Planet 9 could absolutely be there, and previous surveys might just have not been good enough to find it. That's the working assumption among the hunters. They aren't giving up, they're waiting for the next generation of telescopes, and that next generation has now arrived. On a remote mountaintop in northern Chile, at an altitude over 7,000 feet, sits the most ambitious sky survey instrument ever built. It's called the Vera-C Rubin Observatory, named after the American astronomer who provided strong evidence for dark matter in the 1970s. The observatory was decades in the making. Construction began in 2014. Funding came from the National Science Foundation and the Department of Energy, plus private donors. The total construction cost ran to roughly $680 million. The telescope's primary mirror is over 27 feet across. Its design is unique among large telescopes because it combines a huge mirror with an extraordinarily wide field of view. The most jaw-dropping component is the camera. The Rubin camera is the largest digital camera ever built for astronomy. It contains over 3 billion pixels. A single image from this camera covers an area of sky equivalent to 40 full moons. Each exposure takes about 30 seconds. Each night, the telescope captures about 1,000 images. Over the course of its planned 10-year survey, it will photograph the entire southern sky every few nights, building up the most complete moving picture of the heavens ever attempted. The full survey, called the Legacy Survey of Space and Time, started full operations in early 2026, after years of commissioning and testing. Early commissioning images were already producing groundbreaking results. The first early images released in 2025 showed over 2,000 previously unknown asteroids in just a few nights of observing. For Planet 9 hunters, the Rubin Observatory is a dream tool. It surveys the southern sky, where Planet 9 is most likely hiding. It detects faint moving objects with unparalleled sensitivity. Its repeated coverage, every few nights, makes it easy to spot anything that shifts position over time, the telltale sign of a solar system body. Its automated data pipelines compare each new image with previous ones, flagging anything that's moved. A slow-moving planet, drifting along its orbit, would stand out clearly. Mike Brown has called the Rubin Observatory the perfect tool for finding Planet 9. He said publicly that if someone had given him a budget and asked him to design a telescope specifically for this task, he would have built something very close to the Rubin design. Scott Shepard, one of the original co-discoverers of the orbital clustering that started the Planet 9 story, has estimated the observatory has roughly a 70 to 80% chance of finding the planet if it exists. Those odds aren't certainty. There's still a real chance Planet 9 could escape detection, especially if it's at the dim end of the predicted parameters. If the planet is small and currently at the far end of its stretched orbit, even Rubin might struggle to spot it. Brown himself has said that if Rubin doesn't find the planet within a few years, the team will move to using radio telescopes for further searches. But for the first time in a decade, the hunters have a tool that can actually do the job. The combination of wide field, deep sensitivity, frequent revisits, and the perfect viewing location makes the Rubin Observatory the most promising Planet 9 detector ever built. The world is watching. Within a few years, possibly within months, the question of whether Planet 9 exists could finally be answered. But the telescope's capabilities go far beyond just finding one planet. When astronomers talk about the Vera Rubin Observatory's chances of finding Planet 9, they don't usually frame it in terms of decades. They frame it in years. Specifically, the next 2 to 3. The reason is straightforward. The Rubin Observatory's survey is designed to repeatedly cover the entire southern sky. Within the first year of full operations, it will have imaged nearly every patch of accessible sky multiple times. By comparing those images, the telescope's automated systems will identify every slow-moving object brighter than a certain threshold. If Planet 9 is within that threshold, and if it's in the southern sky, it will be found. The threshold matters. The Rubin Observatory can detect objects roughly 24 times fainter than what the human eye could see with a giant telescope decades ago. That's deep enough to catch most of the predicted Planet 9 parameter range. Brown has said publicly that if the telescope finds a slow-moving object at around 500 to 600 Earth-Sun distances, that object is almost certainly Planet 9. Siraj's 2025 paper made the case even more concrete. According to his refined predictions, Planet 9 would fall directly within the field of view of the Rubin Observatory's early observations. Within the first year or two of operations, the telescope would likely catch it. 2027 is the unofficial target. By the end of that year, if Planet 9 exists in roughly the predicted parameters, Rubin should have spotted it. Astronomers will then track the object across multiple nights to confirm its orbit, calculate its mass, and verify that it really is the long-sought hidden giant. The announcement, if it comes, would be one of the most significant astronomical discoveries of the century. But there's a flip side. If Rubin doesn't find Planet 9 within those 2 years, the situation gets uncomfortable. The most plausible parameter range for the planet will have been ruled out. The hunters would have to either expand the search to even smaller, dimmer planets, or conclude that the hypothesis is wrong. Scott Shepard has acknowledged this. The telescope's expected detection probability, around 70 to 80%, leaves a meaningful gap. If the planet is on the small, dark, distant side, Rubin might miss it. In that case, the hunt would continue with even more sensitive instruments in the future, but the case for Planet 9 would weaken with each non-detection. There's a third possibility that's just as interesting. Rubin might not find Planet 9 itself, but it will almost certainly find many more distant icy bodies. The next decade should add hundreds, possibly thousands, of new sednoids and other extreme objects to the catalogue. Each new object provides another data point for testing the orbital clustering hypothesis. With a much larger sample, astronomers will be able to say with high confidence whether the clustering is real or whether it was an artifact of looking at too few objects. If the clustering survives the larger sample, the case for Planet 9, or some hidden mass, becomes much stronger, even without direct detection. If the clustering disappears in the larger sample, then Planet 9's main motivation evaporates. The search would essentially be over. Either way, 2027 could be the end of an era. Either we'll have a new ninth planet in the textbooks, complete with photographs, or we'll have closed the door on a decade-long mystery. The waiting is almost unbearable. After 10 years of arguments, speculation, and increasingly desperate searches, the answer is finally within reach. But the answer might not be a simple yes or no. To appreciate what the Rubin Observatory is doing, picture how astronomy used to work. For most of history, finding a new object in the sky was a slow, painstaking process. An astronomer would point a telescope at a chosen patch of sky, take a long exposure, develop the photograph, and then carefully compare the image to previous ones. This process could take months for a single discovery. Over a lifetime, an astronomer might catalogue a few hundred new objects. The Rubin Observatory does this in a single night. Every clear night, the telescope captures roughly 1,000 images of the sky. Each image covers an area equivalent to about 40 full moons. The combined coverage in a single night reaches several thousand square degrees of sky. Over the course of a few weeks, the observatory effectively maps the entire visible southern sky from horizon to horizon. Then it does it again, and again, and again, over and over for 10 years. The result is a moving picture of the cosmos. Each patch of sky is imaged hundreds of times over the survey's duration. By comparing successive images, the data pipeline identifies every object that moves, varies in brightness, or appears or disappears. Asteroids, comets, supernovas, gamma-ray bursts, variable stars, and yes, distant planets, all show up automatically in the database. The numbers are staggering. The observatory is expected to catalogue roughly 10 billion individual objects over the course of the survey. The total data produced will reach the petabytes, which is thousands of trillions of bytes. The data is encrypted and routed through dedicated networks to a major facility in California, where automated systems sort and analyze it before releasing relevant subsets to the scientific community. For the Planet 9 hunt, the key feature is the slow mover detection capability. A planet at 300 Earth-Sun distances takes thousands of years to orbit the Sunday. From our perspective, it appears nearly stationary in the sky. Over a year, it might shift its position by an amount roughly equivalent to a millionth of a degree. That's a tiny motion, but it's detectable. The Rubin Observatory's image comparison algorithms are designed to spot exactly this kind of slow shift. If Planet 9 is in the southern sky and within the observatory's brightness range, it will appear as a faint dot in successive images, gradually shifting against the fixed background of stars. The data pipeline will flag it. Astronomers will follow up with confirming observations from other telescopes. Within weeks of the first detection, the planet's orbit will start to be characterized. The hunt isn't just about Planet 9. The Rubin Observatory will discover thousands of new, distant, icy bodies. Many will be the largest sample of extreme trans-Neptunian objects ever catalogued. Each one tightens the constraints on what's out there. Each one tests whether the clustering pattern is real or an illusion. Each one provides another piece of the puzzle. There's a fascinating consequence of the survey. Even if Planet 9 doesn't show up directly, the new sample of distant objects will tell us, with high statistical power, whether something is shepherding them. If the patterns hold up in a sample 10 times larger than what we have now, the case for a hidden planet becomes overwhelming. If the patterns break down, the case dissolves. Either outcome would be major news. A decade of speculation will end, either with photographs of a new world or with the realization that we've been chasing a statistical ghost. But what if neither outcome happens? There's a scenario that haunts every Planet 9 believer. Imagine the Rubin Observatory completes its first few years of full operations. The data pours in. The catalogue of distant icy bodies grows by orders of magnitude. The survey reaches deep into the predicted Planet 9 parameter space, and nothing turns up. No matching dot, no slow-moving giant, no telltale signature of a hidden world. What then? The first reaction would be to refine the predictions. Maybe Planet 9 is dimmer than we thought. Maybe it's smaller. Maybe it's farther. Each non-detection narrows the possible parameter space. As the hunt continues, the predicted planet would have to keep shrinking and dimming to remain consistent with the data. At some point, the planet becomes so small or so dim that it can no longer produce the gravitational effects that motivated the hypothesis in the first place. Brown and Batygin would face a tough decision. They could either continue defending a smaller, dimmer Planet 9, hoping that future telescopes might still find it, or they could acknowledge that the hypothesis has been weakened beyond saving. The pressure from the broader astronomy community would grow. Other explanations for the orbital clustering would become more attractive. What might those alternatives be? One possibility is that the clustering is an observational artifact. Our catalogue of distant icy bodies is incomplete and biased. Surveys preferentially find objects in certain orbital configurations and miss others. Some critical analyses have argued that with better data, the apparent clustering might disappear entirely. If Rubin's expanded sample shows that the icy bodies are actually randomly distributed, the Planet 9 motivation collapses. Another possibility involves modified gravity. Some physicists have proposed that gravity might behave slightly differently at very large distances or very low accelerations. These ideas, called modified Newtonian dynamics or related theories, have been used to try to explain galactic rotation curves without invoking dark matter. Some researchers have suggested that modified gravity could also produce the apparent orbital clustering in the outer solar system without any hidden planet. Most astronomers find this explanation unconvincing, but it remains a fringe possibility. A third option is dark matter. Some theorists have proposed that a localized clump of dark matter in the outer solar system could mimic the gravitational effects of Planet 9. This is even more speculative, but it can't be entirely ruled out. A fourth option is that the clustering is a fossil. Maybe long ago, perhaps 4 billion years ago, a passing star or some other event scattered the distant icy bodies onto their current orbits. The clustering would be a historical record of that event, not the result of ongoing shepherding. In that case, no planet is needed today. The patterns would fade over millions of years and would be just slowly dissipating in the present. Each of these alternatives has its own problems. Each one feels less elegant than a hidden planet. But if Planet 9 doesn't show up, the alternatives will get serious attention. There's a more philosophical implication. A null result from Rubin would be a sobering reminder that even our best hypotheses can be wrong. The Planet 9 story has become so widespread, so embraced by the public and the press, that its non-existence would feel like a real loss. Astronomy would have to come to terms with a universe slightly less interesting than we'd hoped, but Brown remains confident. He said publicly that he's extraordinarily confident Planet 9 exists. He's also said the hunt continues either way. New tools, new ideas, new targets. Because there's a possibility most people overlook. Planet 9 isn't even necessarily a planet. There's an idea floating around the edges of the Planet 9 debate that doesn't get nearly as much attention as it should. What if there's no hidden planet at all? What if the orbital clustering of distant icy bodies is telling us something even more profound, that our understanding of gravity itself is incomplete? This idea isn't new. For decades, some physicists have argued that Newton's laws of gravity and even Einstein's general relativity might break down in certain extreme situations. The most famous version is called modified Newtonian dynamics, or MOND for short. It was proposed in the 1980s to explain why stars at the edges of galaxies orbit faster than they should under standard gravity. The standard explanation involves dark matter. MOND skips dark matter and modifies gravity instead. Most astronomers are skeptical of MOND. The evidence for dark matter is strong, and modifying gravity creates problems in other areas of physics. But MOND-style ideas keep popping up whenever some astronomical observation seems to require either a strange new mass or a strange new force. Planet 9 fits this pattern. The orbital clustering of distant icy bodies could be explained by a hidden planet's gravity. It could also, in theory, be explained by gravity behaving slightly differently at the very low accelerations experienced by distant objects. A few researchers have explored this possibility, looking at whether MOND-like modifications could produce the observed orbital patterns without any hidden mass. The math is messy. MOND was originally designed to deal with galactic-scale phenomena, not solar system distances. Adapting it to explain Planet Nine's apparent effects requires assumptions that aren't well supported by other data. Most physicists think this is grasping at straws. The observed effects, they argue, are more cleanly explained by a real, massive object hiding in the dark. But the alternative gives us pause. Even Konstantin Batygin has noted that dark matter and modified gravity are very complicated explanations for what's likely going on. He prefers the simpler hypothesis of a real planet. Most astronomers agree there's a related dark matter alternative worth considering. Some theorists have proposed that the distant solar system might contain a localized clump of dark matter, dense enough to gravitationally influence the icy bodies. Dark matter is mostly distributed evenly throughout galaxies, but local clumps could exist in certain regions. If a clump happened to be sitting in the outer solar system, its gravity could mimic the effects of a hidden planet without there being any actual planet there. This idea has the advantage of being testable, in principle. A dark matter clump would have a different mass distribution than a planet. Its gravitational influence on different icy bodies would vary in subtly different ways. If we had enough data, we could potentially distinguish between a planet and a clump. A third possibility is even more exotic. The primordial black hole idea, mentioned earlier, falls somewhere between a planet and a dark matter clump. It would be a localized mass, just like a planet, but it would be invisible like dark matter. It would behave like a planet in every gravitational sense, but it would never be photographed, no matter how good our telescopes get. If Planet 9 turns out to be a primordial black hole, finding it would require entirely different techniques. Direct imaging would be useless. Gamma-ray observations of dark matter interactions, radio telescope hunts, or even fleet missions of tiny probes might be needed to confirm such a strange object's existence. Brown and Batygin lean toward the simpler planet hypothesis, but they acknowledge that the evidence, so far, is consistent with several different possibilities. Until someone catches the object directly, the door remains open to truly weird answers, and the longer the search drags on without success, the wider that door swings. There's a question that often gets glossed over in Planet 9 discussions, but it's a critical one. When did Planet 9 arrive in its current orbit, and is the timeline consistent with everything else we know about the solar system? The standard scenarios all require Planet 9 to have been thrown into its current configuration during the chaotic early years of the solar system. Within the first few 100 million years after the Sun formed, the gas giants migrated wildly. Smaller planets got scattered. Captures and ejections happened. By the time the giants settled into their final orbits, the basic architecture of the solar system was set. Planet 9, in any of the proposed origin stories, has to fit into this early window. The slingshot model requires the planet to be flung outward by Jupiter or Saturn within the first 100 million years. The capture from a passing star requires a close stellar encounter while the Sun was still in its birth cluster, also within roughly the first 100 million years. The rogue planet capture is harder to date, but most simulations suggest it would have happened relatively early as well. Once Planet 9 is in its current orbit, it has to stay there for the remaining 4.4 billion years of solar system history. Its orbit can't have been disturbed much in that time. It can't have been gradually pushed outward by passing stars to escape velocity. It can't have been pulled inward by other gravitational effects. It needs to have sat patiently, in roughly the same configuration, for the entire age of the solar system. This long-term stability is actually a feature, not a bug. The orbital patterns we see in the distant icy bodies are the result of billions of years of gravitational shepherding. If Planet 9 had been on a different orbit a billion years ago, the patterns wouldn't match what we observe today. The current patterns require a stable, persistent shepherd, but long-term stability has constraints. Planet 9's predicted orbit is at the edge of what's gravitationally stable in the outer solar system. Passing stars, close encounters with other objects, and slow, chaotic effects can all destabilize stretched orbits over billions of years. For Planet 9 to have survived, its orbit has to be in a sweet spot, stable enough to persist, but extreme enough to produce the shepherding effect. Some critics have argued that this sweet spot is too narrow. The probability of a planet being kicked into exactly the right orbit during the early chaos, and then surviving for billions of years without being further perturbed, is uncomfortably small. The odds are estimated at a few percent, depending on exactly which scenario you assume. A few percent isn't impossible, but it does mean Planet 9's existence requires luck, the right kick at the right time, the right stabilizing nudge, the absence of disrupting encounters over billions of years. Each step in the chain has to go right. Defenders of the hypothesis point out that astronomical chains of luck happen all the time. We're here because of countless lucky events in our own planet's history. The odds of any specific solar system architecture are tiny, and yet some specific architecture had to result from the early chaos. Why not Planet 9? The timeline problem doesn't kill the hypothesis. It just adds another layer of uncertainty. If Planet 9 exists, its existence is a happy accident, a survivor of the violent solar system's youth. If it doesn't exist, then we need a different explanation for the orbital patterns, and the alternatives all have their own problems. The cleanest test, again, is direct detection. If we find the planet, all the timeline questions become fascinating problems to solve. If we don't, we'll be stuck speculating for years. But Planet 9's reach might extend even further than we've discussed. It might touch the very edge of the Sun's gravitational influence. Far beyond the Kuiper Belt, well past where Planet 9 is thought to live, lies the most distant region, still under the Sun's gravitational sway. It's called the Oort cloud. Unlike the flat Kuiper Belt, the Oort cloud is a vast spherical shell of icy worlds surrounding the entire solar system. It extends from roughly 2,000 Earth-Sun distances out to perhaps 100,000 Earth-Sun distances. The far edge of the Oort cloud is so far away that the Sun is barely brighter than a typical star at that distance. The Oort cloud is the primary source of long-period comets. These are comets whose orbits take them on enormous loops, sometimes lasting millions of years per circuit. They occasionally fall inward toward the Sun, develop bright tails, and put on shows for inner solar system observers before swinging back out into the depths. For a long time, the Oort cloud was assumed to be roughly spherical. Comets were thought to fall inward more or less randomly, with no preferred direction. Recent observations have complicated this picture. Some studies suggest that long-period comets show subtle directional preferences that could be explained by gravitational influences from a hidden, distant planet. If Planet 9 is real, its gravity would slightly bias the orbits of comets in the inner Oort cloud. Over billions of years, these biases would accumulate. The result would be a non-random distribution of comet orbits, with certain directions preferred and others suppressed. The patterns would be subtle, but detectable with enough data. Some astronomers have looked for these patterns, with mixed results. The data is noisy. The sample of well-characterized long-period comets is small. Different analyses have come to different conclusions. Some find evidence for a Planet 9 influence on the cometary population. Others find no significant effect. The issue is partly statistical. Long-period comets are rare. They're hard to catch and characterize. Their orbits, calculated from limited observations, often have large uncertainties. Drawing conclusions about the underlying population is difficult. The Rubin Observatory will help here too. Its repeated coverage of the southern sky should detect many new long-period comets over the next decade. Each comet adds to the statistical sample. With a much larger and better characterized population, astronomers will be able to test more rigorously whether there's a hidden gravitational bias from a distant planet. There's an even stranger possibility lurking in this idea. If Planet 9 has been gently nudging Oort cloud comets for billions of years, it might occasionally have steered comets toward the inner solar system. Some of those comets would have impacted Earth or other planets. A few researchers have speculated that major impact events in Earth's history could have been triggered by Planet 9's gravitational interactions with the cometary population. This is highly speculative. There's no direct evidence linking Planet 9 to specific impact events in Earth's past. The idea is more of a thought experiment than a serious scientific claim, but it illustrates how a hidden planet might affect even our own planet's history in subtle ways. The connection to the Oort cloud also reminds us of how vast our solar system actually is. Planet 9, at 300 Earth-Sun distances, isn't even halfway to the inner edge of the Oort cloud. The Oort cloud itself is enormous. The total volume of space under the Sun's gravitational influence dwarfs anything we typically picture when we think of the solar system. In all that vast space, hidden planets could easily lurk. Planet 9 might be just the first. If we did finally see it up close, what would we be looking at? Suppose, somehow, you could travel to Planet 9. Suppose a future spacecraft, accelerated to astonishing speeds, could close the gap and arrive at the hidden world. What would you see? The journey itself would be staggering, even at the speed of NASA's New Horizons probe, which flew past Pluto in 2015. Reaching Planet 9 at 300 Earth-Sun distances would take centuries. With more advanced propulsion systems that don't yet exist, the trip might be reduced to a few decades. Either way, sending a probe to Planet 9 is a multi-generational undertaking. When your probe finally arrived, it would find a world like nothing humans have ever visited. Planet 9, if it's the rocky body that recent simulations suggest, would be roughly 4 times the mass of Earth. Its diameter might be about 1.5 times Earth's. Its surface gravity would be perhaps twice as strong as Earth's. Standing on it, you'd weigh about twice what you weigh now. The Sun, from Planet 9's surface, would be barely more than a bright star. Sunlight would reach the planet at about 1/90,000th of the intensity we get on Earth. Daytime would be a cold, grey gloom barely brighter than a moonlit night on Earth. Photographs taken from the planet's surface would look almost completely black except for the brightest stars. Temperatures would be brutally cold. Without much heat from the Sun, Planet 9's surface would hover near absolute zero. We're talking about -400 Fahrenheit or colder. At those temperatures, most familiar substances behave in unfamiliar ways. Nitrogen freezes into solid ice. Methane and other simple compounds form rocky hard glaciers. The atmosphere, if Planet 9 has one, might consist of frozen layers of substances that we usually only encounter as gases on Earth. The terrain would depend on the planet's history. If Planet 9 formed in the inner solar system before being flung outward, it might have a rocky surface similar to Earth's, perhaps battered by ancient impacts and frozen volcanoes. If it picked up icy material during its long exile, the surface might be coated in slowly accumulated frost. There could be vast plains of frozen nitrogen, methane glaciers that flow imperceptibly slowly, and shadowy basins where temperatures drop even further. The sky would be eerie. The stars would shine as they do anywhere in the universe, since they're all so far away that Planet 9's location doesn't change them. The Sun, by contrast, would be a small, bright point. The other planets, if visible at all, would be tiny dots scattered across the sky. Earth, from Planet 9, would be lost in the glare of the Sun and effectively invisible. If Planet 9 has any moons, they'd be the most spectacular sight in the local sky, captured during the planet's violent past, or formed alongside it. The moons would appear as significant disks against the dim starlight. Whether Planet 9 has moons is unknown. Many planets at similar distances do have small companion bodies, so it's plausible. What about life? Planet 9, frozen and dark, is one of the least promising places in the solar system to look for biology. Without sunlight, photosynthesis is impossible. Without internal heat, geological activity that might support deep rock biology is doubtful. The planet's surface is essentially a dead, frozen wasteland. But subsurface conditions could be different. If Planet 9 has any internal heat from radioactive decay or residual primordial warmth, it might harbor a subsurface ocean of liquid water, similar to what's been found beneath the icy crust of Jupiter's moon Europa. Such an ocean, if it exists, could potentially support extremophile microbes. It's a long shot, but it's not impossible. Planet 9 might be lonely, frozen, and forbidding, but it's still a world, and if it exists, it's ours. For years, the Planet 9 debate has focused on a single hidden world. Either it's there or it isn't. But the more astronomers study the outer solar system, the more they suspect that the answer might be even stranger. Maybe there isn't just one hidden planet. Maybe there are several. The Planet Y proposal from late 2025 was the first major hint. If Siraj's analysis of Kuiper Belt orbits is correct, there's a separate, smaller, closer hidden world tugging on the inner Kuiper Belt. Planet Y wouldn't replace Planet 9. The two would coexist, each one explaining different orbital patterns. The idea of multiple hidden planets isn't new. Some theorists have argued for years that the outer solar system might harbor several undiscovered worlds. The original solar system was a chaotic environment, with many planet-sized bodies forming and being scattered around. Computer simulations suggest that the early outer solar system might have had as many as 5 or 6 giant planets, not just the 4 we see today. Some of those extra planets were ejected entirely, but some might have ended up in stable, distant orbits that we haven't yet detected. The Vera Rubin Observatory should be able to tell us. If multiple hidden planets exist within a few hundred Earth-Sun distances, the survey will probably catch them. Each new detection would tighten our understanding of the outer solar system's true architecture. There's a tantalizing possibility that the cascade could go even further. Beyond Planet 9, beyond Planet Y, in the deeper reaches of the outer solar system, there could be even more hidden worlds. Some might be Mars-sized rocky bodies. Some might be smaller dwarf planets. The deep outer solar system, between roughly 500 and 2,000 Earth-Sun distances, is essentially unexplored. We have no good catalogue of objects out there. Anything could be hiding. Imagine the implications. If our solar system contains, say, a dozen previously unknown major bodies, we'd have to fundamentally rewrite our understanding of how solar systems form and evolve. Our cosmic neighborhood would be far more crowded and complex than anyone realized. The neat 8-planet portrait taught in schools would be a quaint oversimplification of a much wilder reality. The cascade idea also has implications for other star systems. If our solar system harbors hidden planets beyond what we've catalogued, then most or all star systems probably do too. The exoplanet surveys of recent decades have found thousands of planets around other stars, but they've been biased toward planets close to their host stars. The far outer regions of those systems are essentially invisible to us. There could be hidden planets out there too, by the millions or billions, scattered across the galaxy. This bigger picture is humbling. It suggests that we've barely scratched the surface of understanding what's actually in our cosmic backyard, let alone the wider universe. The simple architecture of our solar system that we thought we understood for centuries might be a deeply incomplete picture. There's a positive side to this realization. If hidden planets are common, then the discovery of one in our own solar system isn't a fluke. It's a representative sample of what's normal. Each hidden planet we find teaches us about a population of similar worlds throughout the galaxy. The hunt for Planet 9, in this light, isn't just about adding a 9th body to the textbooks. It's about opening a new chapter in our understanding of solar systems generally. The first hidden world we find could be just the beginning of a much broader exploration. What comes after that exploration could change everything we thought we knew about how planets and their stars work together. Step back from Planet 9 for a moment. The hunt for a hidden world in our solar system isn't just a local mystery. It's a window into something much larger. For the past 3 decades, astronomers have been finding planets around other stars at a remarkable pace. The first confirmed exoplanet around a normal star was discovered in 1995. By 2026, the catalogue has grown to several thousand. We've found planets in nearly every configuration imaginable. Hot Jupiters that orbit their stars in just a few days. Super-Earths that might harbour liquid water. Rogue planets drifting alone through interstellar space. Planets in binary star systems. Planets in triple star systems. Planets so far from their stars that their orbits take centuries. Yet for all this progress, we've barely scratched the surface. Our exoplanet detection methods are biased toward planets close to their host stars. Distant, slow-orbiting planets are nearly invisible to us. We see the inner regions of other solar systems clearly, but the outer regions, where Planet 9 analogues might lurk, remain dark. If Planet 9 exists in our system, it almost certainly has cousins around other stars. The mechanisms that put it on its strange orbit, whether scattering, capture, or rogue capture, must operate around other stars too. Wide-orbit planets aren't a fluke, they're a category. Each star system probably hosts a few. Across the galaxy, the number of these distant hidden planets must run into the billion. This realization changes how we think about planet formation. The standard picture, where planets form quietly in flat protoplanetary disks and stay roughly where they were born, was always too neat. Real solar systems are chaotic. Planets migrate. They get scattered. They get captured. They get ejected. The architecture we see today is the result of billions of years of dynamic interactions, not a static blueprint. Planet 9, if confirmed, would be a powerful reminder of this chaos. It would be a visible relic of the violent youth of our solar system. Its strange orbit would tell us about the gravitational mugging it suffered billions of years ago. Its very existence would prove that solar systems are more dynamic, more interesting, and more bizarre than we'd assumed. There's a deeper philosophical implication. If our own solar system, after centuries of careful study, still hides a major planet from us, what else might be out there? What other features of the cosmos are we missing because they're slightly too dim, slightly too far, slightly too unusual to fit our existing search techniques? The Planet 9 story is a reminder that the universe is bigger and stranger than our methods can easily reveal. Discovery, when it finally comes, will probably be anticlimactic, a faint dot, a slow shift in successive images, a press conference, photographs. The textbooks will be updated. School children will learn that the solar system has 9 planets again. The world will move on, but the implications will linger. Each new discovery in the outer solar system will be filtered through the question of what else might be out there. Each strange exoplanet found around a distant star will be compared to Planet 9. The hunt that started with 6 aligned icy bodies in 2014 will have permanently shifted our understanding of what a solar system can be. And somewhere, billions of years from now, when our sun has died and the planets have scattered, Planet 9 will still be drifting through the dark, a frozen, rocky exile, finally freed from its long, lonely orbit, wandering through interstellar space as a true rogue at last. A fitting end for a planet that almost wasn't ours to begin with.